Welcome. I want to welcome you all back, and I want to say thank you for such the large amount of views my last video got. Um, I got like 9 views, and I was really surprised to see that, as most of my videos get like 2. So, I want to say thank you for that. But other than that, I want to get started. So, in today's video, we're going to primarily talk about inverse functions and logarithms. And the next video we're going to talk about the inverse trig functions, as if I were to talk about those, I feel like this video is going to become too long. My trig video was an hour long and it only got like 2 views, so I don't want to do that again. But to get started, an inverse function is a function that will take on an input y and output x. So we remember with a normal function that it's going to take an input x and output y, really. So what this is really saying is we're going to take an input x and it's going to correspond to exactly one output y, and this is what f does. But what f inverse does is it's going to take one input y and it will correspond to one input x. In fact, since it's the inverse of an original function, it's going to be the same input x of f that gets output by f inverse of x. And we'll talk a bit more about that here in a moment. So, how do we know or what is a one-to-one function? Let's start out there. A one-to-one function is a function is a function that has the property that no two f of x's, so f of x1, can never be equal to another f of x. And how can we tell this, really? Well, if we're looking on a graph, there is a test known as the horizontal line test. Horizontal line test, which will tell us that if we draw in a horizontal line, and if it intersects the curve at more than one point, then the function will not have an inverse. That is a function specifically. But this doesn't work very well with tables. Well, let's look at this table that we have, and we are going to determine whether or not it's a function. And I'll give you a moment. And if you've taken a moment to look at the table, you'll see that P of 0, which I'm just saying population times 0, is equal to 100. And population at 5 is equal to 100. So no, this function here is not invertible, or does not have an inverse. Not have a inverse. Continuing on, this graph of the parabola that we have, we use the horizontal line test, and we'll see again that it intersects the curve at more than one point, if my pen wants to draw it. So no, this does not have an inverse. Have a inverse. Alright, continuing on. Are the following functions one-to-one? So all of these are graphs, and I'll show you in a very short while how we can derive whether or not a function is one-to-one. And I'll give you a moment to think through this yourself. And what we'll see is this first function is invertible, or does have an inverse. Have a inverse. And this is because it passes the horizontal line test. No matter where I draw a horizontal line, it will only intersect it once. For the second one, since I have assumed that you've probably worked through all of these, this is not invertible because it fails the horizontal line test. Not invertible because it fails the horizontal line test. And you can abbreviate the horizontal line test to HLZ, and this is common math notation if I remember correctly. It might also be one of my old teachers' made-up notation, but I think that can widely be recognized as the horizontal line test. Continuing on, we have a sinoid curve, and the issue with sinoid curves is they are indefinitely repeating, or sinoidal curves, so it's bound to fail the horizontal line test. So this is also not invertible. Sorry about my horrible handwriting, because it fails the horizontal line test. HLZ. Now, this bottom one here is an exponential function. And what we'll see is that this exponential function does indeed have an inverse as it passes this horizontal line test. And this is going to be one of the big topics of today. What is the inverse of an exponential? And we'll get to that in just a moment. But yes, this does have an inverse. An inverse passes the horizontal line test. Okay. So the true definition of an inverse function is a one-to-one function with domain D and range. If f is a one-to-one function with a domain D and a range E, then the inverse of f is denoted as f inverse will have domain E and range D. So once again, I've drawn the original diagram that I drew for you, and if you'll see, look at it, you'll notice that whenever we're taking something from the element D, it's going to correspond to something in the element E, and that's going to be our Y. And whenever we take something from E and it corresponds to something in D, that's going to be our X. So really what we can do with this is, because f inverse of y is equal to x, and we know y is equal to f of x, we can derive that f inverse of f of x is equal to x. Continuing on, I've actually got us some problems here. So if we're looking at this and we know what an inverse is, what would f inverse, or I'll give you a moment, maybe think about these in your head. And now that you've had a moment, what would f inverse of 7 be if f of 2 is 7? Well, this is just the y value here, 7, so that would mean it corresponds to the x value, 2. Once again, this is our y value, and this is our y value, or the output of g. Oh, this should be g inverse. And this should also be g inverse, although I wanted it to originally be 8, but I'm not going to change that. So this is our y value, or our output for g. And this over here is also our output, but we can see our input was 6, so this means that our output's going to be 6. And g, or pi, is going to be g of 9, so our output y is pi. And our input into our g inverse is once again going to be pi. We would see that it's going to output 9. Alright, continuing on, let's look at the inverse graphically. And I'm going to change colors for this. So, if I was to just ask you, what does the inverse do graphically? Well, it flips the graph f of x over the line y is equal to x. So what the new graph is going to look like for, let's say, this f of x on the left here, it's going to look like a reflection. Although my or my drawing skills aren't the best, but you can see the point. It has its signature first curve, it has its indent, and then it goes back out. Now, what this really does, or what this means, is that for any point, let's say that this point right here is x1 f of x. Well, the corresponding point on this graph would look like f of x, x1. And that's what the inverse does graphically. It swaps your x values, and then it makes your x values your y values, and then it's going to make your y values your x values. So now I have another graph. In fact, this is a cubic function, more specifically x cubed plus 3. So if we wanted to draw the inverse of this graph, what we would see is, well, we will have a point at 2, -1. So let's draw that point in at 2, -1. We also know that there's going to be a point at 0, 3. I have to draw in a slant because it sometimes doesn't like things. And then finally, we know that there's going to be a point at 4, 1. So what this graph's going to look like is it's going to look something on the lines of this. A nice little swirl. Let's continue. To find the inverse algebraically is not really that difficult. So what we do is we have a step process. We are going to swap the x's and we're going to swap the y's in a function. And then we're going to solve for y once you get solve for y. And once you get y by itself, you will have the inverse, and the inverse, it's inverse, and the inverse is, nope, it's fine. You will have its, oh, never mind. This is a question. You will have its inverse, period. Apparently I need to go back to grammar. Now. So I'll work on the first example with you, and then I'll give you a few moments to work on the other examples, and then I'll go over the answers. Okay, so for this first function, we are going to swap its y's and its x's, so x is equal to y cubed plus 4. So then we're going to subtract that over. So we're going to get y cubed is going to be equal to x minus 4. So y is going to be equal to the cube root of x minus 4. Now, take your time, work through the following things, and we'll go through this one together. So now that we're back, you'll see that I've worked through all of these problems. But you may have noticed that these bottom two, well, let's first work on the top one. So we first start by swapping the x and the y, so we get x is equal to y over 4. And then we can now solve for y, just multiply both sides by 4, and we get y is equal to 4x. But for the second one that you did, whenever you swap the x's and the y's, you can't actually get y by itself. And what this tells us is that the original function was not invertible. And the same thing goes for this y is equal to 5 to the power of x. But wait a minute, didn't we say that was invertible earlier? Since it is 1-to-1? Well, it is. We just don't have the tools to invert it yet. And that's what we're going to be doing in this next section. But I would like to solve or find the difference quotient for the inverse of x plus 2. So, to start out, we need to find the inverse. So, y is y is equal to the square root of x plus 2. So, y squared, I want to say x is equal to the square root of y plus 2. So, we can square both sides, and we would get x squared is equal to y plus 2. So y is equal to x squared minus 2. So we are now only halfway through the battle. Now we have to apply our difference quotient. Although I'm almost out of space. Nope, I can't. Okay, I should be able to work under that. So the difference quotient, if we remember, is going to be f of x plus h minus f of x all over h. So what this is going to look like on our what this is going to look like is we're going to have x plus h squared minus 2 minus x squared plus 2 all over h. Well, we can now square this term out, so we're going to get x squared plus 2xh plus h squared minus 2 minus x squared plus 2 all over h. So we can cancel some terms, so we can get rid of this negative x squared and this x squared, and this negative 2 and the positive 2, and we're left with 2xh plus h squared all over h, or we are just left with 2x plus h. And that would be the difference quotient of the inverse. And you might notice that I am beating this difference quotient in. I think I've only done 2 videos so far where I haven't done a difference quotient. And you'll understand why once we reach the next unit. But let's continue. I want to start with a question. How do we find the inverse of an exponential? Well, let's start. We know that whenever we start, we start with y is equal to b to the x. Well, how can we get rid of this or swap it? So we have x is equal to b to the y. But how do we get the y out of the exponent? Well, we have a nifty little tool. Let's define a new function. So the logarithm of a base is the inverse of the base. So if we have this and our input is y, and this is an inverse, this is just y. However, we have to take the log of both sides so it remains equal. So we get the log base b of x. So our final function is actually log base b of x. Ooh, and this has a ton of useful it is a very useful tool in logarithms. They are used heavily to solve exponentials. So, let's work on some problems now. And I'll give you a moment. If you want, you can try to find the inverses of these yourself. I'll give you one hint. One of these is not invertible. Well, I'll give you that moment. And then whenever we return, we'll walk through the answers. Okay, in order to find the first one, we are going to start by once again swapping our y's. And this time we're using t as our variable, but that doesn't matter. So it's going to be t is equal to 8 times by 3 to the y minus 1. So t divided by 8 is going to be 3y minus 1. Now we can take the log base 3 of both sides. So t over 8 is equal to y minus 1. Remember, log base 3 is going to be undoing this term, this constant, and just bringing down the y minus 1. So what we're going to be left with is y is equal to log base 3 of t over 8 plus 1. Continuing on to this next problem, once again we swap the variables, so t is equal to 4 times by 6 to the y plus 4. So then we get t over 4 is equal to 6 to the power of y plus 4. Take the log base 6 of both sides this time, of t to the over 4 is equal to y plus 4. So really, log base 6 of t over 4 minus 4 is equal to y. And that's our inverse. Now for this final one, we can already tell it won't have an inverse, but let's try it. So t. I'm sorry, my throat's not doing the best today. T is equal to 6y squared plus 3 all over 3. Well, we're going to multiply the 3 over, so we get 3t is equal to 6y squared plus 3. We can now take the log base 6 of both sides, and we'd get y squared plus 3. So we can now get log base 6 of 3t minus 3 is equal to y squared. But we have a y squared, so if we take the square root of that, we have to take both the positive and the negative square roots. And as thus, this is not a function, as it will have two different values of y for any input t. Continuing on, let's look at some properties of logarithms. So logarithms have properties that make them a bit easier to work with. So for example, log base b of x plus log base b of y is log base b of x times y. Log base b of x over y is equal to log base b of x minus log base b of y. Log base b of x to the power of r is equal to r times log base b of x. And the log base b of b is equal to 1. Where b is really any number, except for b cannot be equal to 1. Well, inside here it can be equal to 1, but inside here it can't. No, does not. Yeah. Let's see. I'll give you a moment. If you want, you can try to expand this out yourself, but I will do it. Take your time, and I'll be back in just a moment. Alright, let's do this. So if we want to expand this out, we will first look at the first term. Well, we are multiplying something, so we can do log base b, I really should have used numbers for this, log base b and b down there as well, of x cubed plus the log base b of x to the fourth plus 3. I'm going to move this now to the left side. Minus log base b of x squared. Now we can also bring the exponents out in front. So we would get 3 log base b of x plus 4 log base b of x to the fourth plus 3 minus log base b, or 2 log base b of x. And what we can see is that this is actually going to simplify down to log base b of x plus 4 log base b of x to the fourth plus 3. Now let's erase this and work on the next one. Okay. Slowly but surely erasing everything. Okay, now we have a bit simpler one. So the numerator is just going to be log base b of x plus 1, in parentheses, minus, because we're dividing, the log base b of cosine of x. Alrighty. Well, now let's look at how we can condense logarithms like this. Well, let's start. We'll work our way left to right. So we have log base. That was a horrible log. Log base b, and we can multiply the end side of the parentheses of these functions. So we'd get x squared plus x. And now we just have the log base b of x squared plus x. Oh, wait! That cancels. It's 0. What a wonderful problem thought out by me. Alright. Let's look at the exponential graphically for a moment. Well, all exponentials will go through the point 0, 1, as long as they have not been shifted, and they will look something on the lines of y is equal to b to the x. This line that I've drawn out is y is equal to x. I've drawn out this line, and we are going to see that the logarithm is going to be a perfect mirror of this function. So it's just y is equal to log base b of x. And you'll see they're perfect mirrors of each other on the graph. In fact, their domains are perfectly swapped. The domain, or I'll do this domain in pink because it is pink. So the domain for y is equal to b to the x is all real numbers. And its range is going to be 0 to infinity, not including either. However, for the natural logarithm, or for the logarithm, not the natural logarithm, even though the natural logarithm has the same rule, the domain is 0 to infinity, and its range, I wanted to do that in blue. Domain, 0 to infinity, range, all real numbers. And what you'll see is that with all inverse functions, once again, sounds like I'm beating something out of like a child. I don't beat children, though. look, its domain and its range will always swap. The number e, again, has very special properties. And in fact, we want to work with the number e whenever we're in logarithms. So, the log base e of x is the natural logarithm. And we often want to work in the natural logarithm because, especially for calculus, it's going to have some very, very nice properties, especially dealing with things like rate of change. How can we convert a logarithm of base b to a logarithm to the natural logarithm? Well, the logarithm of base b of x is the same thing as the natural log of x divided by the natural logarithm of b. So I've got some example problems for us. So log base 10 is, or just this log symbol, will normally mean log base 10 of x. Some textbooks will use that as a way to represent the natural logarithm. However, I am going to be saying that log is equal to log base 10. So if we want to convert this, we know that this is going to have a natural log of x in the numerator, but in the denominator, it's going to have a natural log of 10. For this next one, it looks very complicated, but it's just going to be the natural log of 7x plus 4 all over the natural log of pi. And I'll give you a moment. Maybe you want to try this last one by yourself. Don't worry if you don't fully write it out, but I'd like you to, as it's very helpful with properties of exponents. And what you'll see is, after I give you a moment, okay, we'll start, that this is going to be the natural log of the square root of x plus 1 over the natural log of 3, but there's one last thing we can do. We can bring this out, the radical out, because it's the same thing as raising it to the to the 1/2 power. So we are going to get the natural log of x plus 1 is equal to 2 natural logs of 3, or divided by 2 natural log of 3. Apologies, I misspoke. But this is all I have for you today. I want to thank y'all for joining me. I hope y'all have found this video informative, and I hope y'all have a wonderful rest of your day. Bye-bye.